Okay, in this video lecture number 5, I'm going to be talking about scientific reliability and validity. That's scientific reliability and validity. Now, these words, reliability and validity, of course, they're common words and people use them in all kinds of contexts. You'll see that when we cover the Daubert trilogy cases on the admissibility of scientific and technical evidence in court, we'll see that the Supreme Court in Daubert defined evidentiary reliability in this context by referring to the underlying scientific validity of the proffered testimony there in that case and in all future cases. Now, obviously, the law is concerned about the reliability of evidence, the reliability of all evidence. And in your evidence classes, you did or you will be talking about how most, if not all, of our rules of evidence have underlying them the goal of ensuring evidentiary reliability. So in many contexts in evidence, like the hearsay exceptions, for example, we in the law use sort of the standard definition that, well, reliable really means trustworthy. And frankly, if you asked most people in the law or people in the general population, what reliability means, what validity means, they might come up with a definition pretty close to trustworthiness. And in fact, if you ask them what reliability or validity meant, they actually might define it using the opposite word. So reliable means trustworthy, valid means reliable, right? But in the scientific evidence context, the Daubert court said, well, in scientific evidence, reliable expert testimony is determined by the underlying validity of the science or expertise involved. So both in the law and in society in general, these words reliability and validity are thrown around a lot with different meanings in different contexts. But in the scientific community, which is what we're concerned about here, there are very specific definitions for these two words and concepts, and we have to keep those in mind when we are speaking in scientific terms about reliability and validity. So in science, the short definitions are that reliable means consistent, and valid, on the other hand, means true. Okay, so starting with reliability in science. A variable is reliably defined if you keep getting the same value every time you measure it. So reliability of a scientific test, reliability of a measurement device means its ability to obtain consistent results. And there are some different interesting subtypes of reliability. Two interesting ones are intra-rater reliability and inter-rater reliability that I have on the slide. So starting here with intra-rater reliability, that basically just means that if you have the same person measuring something, if you have intra-rater reliability, that means that the same person will get the same result every time a particular variable is measured. So that's really a measure of whether the one rater you're looking at is reliable in terms of his or her ability to consistently measure something. Inter-rater reliability, on the other hand, refers to the degree of agreement between two independent people on a measurement. Two independent people supposedly using the same metrics to measure something. So figure skating is a great example. When all of the judges of an Olympic figure skating event hold up the same or very similar numbers, here's a picture of that down here, we say there's good inter-rater reliability. And of course, if the scores vary quite a bit, like you see down here in this picture, we'd say there was poor inter-rater reliability, right? And we're going to talk a little bit about this inter-rater reliability problem and concern when we discuss Lenore Walker's research protocol on battered woman syndrome. Now, Lenore Walker used different interviewers to interview study subjects, and they were asking research subjects, first of all, very leading questions, which was a problem. That was already a reliability risk. But then she also had those interviewers decide personally whether a particular subject showed evidence of being in a cyclical, violent relationship. Now, there was way too much left up to the subjective impressions there of the interviewers without a lot of clear indications what interviewers did or were supposed to take into account. So there were a lot of inter-rater reliability concerns there with what Lenore Walker did on battered woman syndrome. And then the last one I have listed on the slide that I wanted to highlight is test-retest reliability, another interesting one. This refers to the relationship between a score a person gets on one occasion on some variable and the score he or she gets on a subsequent occasion, and when you're doing a particular test. So the LSAT, for example, one that is near and dear to all of our hearts as lawyers, that actually has fairly good test-retest reliability. So in general, the score a person receives on one administration of the LSAT is going to be pretty close to the score received on a second try, all things being equal, right? Assuming that the person felt, well the day of the test and such. Okay, next, though, we want to talk about validity in the scientific context. So validity refers to the ability of a scientific test to accurately measure what it purports to measure. Does the scientific test or measurement really measure accurately the thing that the scientist says she wants to measure with it? Now, a simple example here would be if someone had a wooden yardstick and she wanted to measure something in yards. Now, a yards, as you know, is 36 inches long. But if that wooden yardstick she was using turned out to actually be 35 inches long instead of 36 inches, then that, in fact, would not be a valid way to measure in yards. She would think she was measuring in yards, but she'd be wrong. All of her measurements there would be invalid. Now, validity and reliability interact in some really interesting ways. So think about this concept, for example. In order to have validity, you have to have reliability. But not every reliable test will be valid. You have to have reliability to have validity, but reliability alone doesn't guarantee validity. So I have two examples here on the slide. A valid thermometer accurately measures air temperature, and it also does so consistently, so it's also reliable. But if you had a thermometer that always measured 10 degrees too high, that's going to be consistently inaccurate. It's going to be reliable because it always measures 10 degrees too high, but it's going to be invalid because it's not accurate. And the same thing with a bathroom scale. Now, I have a bathroom scale that seems to be malfunctioning and measuring my weight consistently 20 pounds more than I weigh. Now, I know I really weigh 20 pounds less because it's right there on my driver's license. So I would say my scale is reliable, but I suspect it's not valid. And again, yes, this is supposed to be a joke. It's supposed to be funny. Just another example of something that can be reliable but not valid. So once again, in science, reliable means consistent, and a variable is reliably defined if you keep getting the same value every time you measure it. And valid means true, so validity of a particular scientific method or test or even study design refers to whether the test or methodology or measuring method accurately measures what it purports to measure. And I would say in order to have validity, you have to have reliability, but not every reliable test or measure will be valid. Now here's an interesting set of diagrams of what look like dartboards that I think illustrates the interplay between reliability and validity. So imagine here that all these black dots on these diagrams are data points, measurements of the same variable, the same one variable measured over and over right in a row. Also imagine that the real true value of the variable here is in the very center of each of these diagrams. The true accurate value is the center, the bullseye position here. So if your test was truly measuring the correct value, we'd want to see that measurement show up right there in the center. All right, now let's look at all these 4 diagrams. So first, on the left here, we have diagram number 1. And what do we see? It shows all the data points bunched up really close together. So our measurement system that we used here definitely seems pretty reliable, right? Since all of the measurements came out pretty close to the same. But this measurement system is clearly not a valid measurement system, right? Because the data points here are all some distance away from the true value at the center. So reliable, but not valid. All right, now diagram number 2 shows that these data points are scattered all around the diagram, right? But they're distributed kind of evenly all around. In fact, if we took an average of all those measurements, we might end up with an average that hits pretty close to the center, to the true measurement. So this is why the diagram lists this measurement system as being valid, because even though the data points are scattered all around the true value, the average of them would probably be pretty close. But of course, this measuring system is not at all reliable, right? Because you're measuring the same variable all these times, and look how far apart your measured values are. So it's not reliable. Now, I know earlier I said you could not have a valid measurement device that wasn't reliable, and this diagram number 2 says that you do have validity without reliability. But the truth really is that you wouldn't want to, as a scientist, use this measurement system here to measure your data points, because in real research, you're not going to be measuring the exact same data point over and over and over and over 20 times. You're only measuring each data point once in all likelihood. So you as a scientist would not want to take a chance on a measurement system that was this unreliable. Okay, next in diagram 3, now we see a measurement system that is neither reliable nor valid. The points here spread all over the place, right? So not reliable clearly, but also they're not evenly spread all around the center true value, right? They're all skewed over here to one side. So clearly not valid either, not reliable and not valid. And then in the last diagram, of course, we finally see data points that are clustered very close together, and they're clustered very close around the true value. So we know that the measurement system used here was both reliable and valid. Okay, so now let's just take a quick look at the interaction between operational definition, validity, and reliability. I think it should be clear to you that validity is going to be related to operational definition, but they are different. So operational definition only means that a variable is clearly defined, that you know how it was actually measured. But validity means that the measurement is not just clearly defined. It is clearly defined, but it's also true. Thus, it's a good choice for a measurement. Now, the example I have on this slide might be a little silly, but I think it gets the point across. So let's say we are a scientist. We want to measure IQ, intelligence quotient for our research. So we might say, well, we're going to use hat size to measure IQ. So the bigger your head, the higher your IQ. Now, my husband and oldest daughter have very big heads, so they would love this measurement of IQ. All right, so let's look at our 3 concepts: reliability, operational definition, and validity. And so what we see here is that, well, measuring IQ by hat size probably going to be very reliable in that different people measuring you with a tape measure are going to come in with about the same size no matter how many times they measure. The same person, for that matter, measuring you over and over with a tape measure, probably going to come in at about the same size. So it's going to be reliable. It's going to be consistent, right? Now, secondly, we can operationally define IQ as hat size. That's a clear definition, right? Anyone reading the methods section of our published paper would understand how we defined IQ, but this measure would be totally invalid, right? Since hat size actually bears no relationship to IQ. Okay, that is the end of video lecture number 5.